be connected in star or delta, that's a single unit of three-phase transformer, or as a three-phase transformer single unit. This will actually save on the cost, so less costly. Whereas if I look at three single-phase transformers connected ultimately as a three-phase transformer, okay, so this will be connected in three-phase configuration. This will be generally more costly or costlier. That is because you are essentially looking at individual units separately being bought and connected as per your requirement. You have more flexibility, clearly. So because of which you may not be able to save on the core cost or the stamping cost or even the winding cost in all probability. So this is generally used whenever I'm going to have extremely large rating. When I have very, very large rating and I want to kind of retain the flexibility to, connect it in either star or delta configuration. So when I look at the single phase transformer being connected as a three-phase transformer unit, the major advantage, as I told you, one is flexibility. Second is the portability is better, because if I have three-phase units together, it will be extremely bulky. Imagine a 400 MVA transformer. It is going to have, each of them is going to have about 150 MVA rating. Each single phase is going to have 150 MVA rating. Obviously, transporting a 150 MVA transformer will be simpler as compared to transporting one single 400 MVA transformer. So, definitely, we are essentially retaining. So, advantages, if I try to write it, I should say advantages of this configuration are portability, flexibility, and one more thing I might mention is, let us say I have three single phase transformer. When I want to store some backup in the inventory, if something goes wrong, I would like to replace maybe one of the single phase units by a good unit. So in that case, I can simply save only a single phase unit. I don't have to save a complete three phase unit. To save a complete three phase unit, it will be definitely more expensive. But on the other hand, if I actually store even couple of single phase units, it will be less expensive and I would be able to replace, whatever is the phase that has conked out, I can replace that by one particular single phase unit. So obviously, inventory when I try to store as a backup, so storage as a backup, that is also simpler when I am looking at single phase units. So generally in many of the power stations you would see that single phase units are connected as three phase transformer bank ultimately. So if I talk about, let us say, a 100 kVA single phase transformer, maybe 400 divided by 230 volts, maybe, just I'm arbitrarily taking. So this is a single phase transformer. Then if I am connecting all these three in three phase configuration, I'm going to have overall kVA rating of the three phase unit will be, or three phase bank will be 300 kVA, because 3 times whatever is the single phase unit. Directly you can multiply, because each of them will be able to handle a kVA corresponding to the single phase kVA rating. So I can multiply that by 3 and then say that is what is my three phase. And if I am connecting, for example, this in star-star configuration, for example. So I am going to have again for the star-star three-phase transformer, the kVA rating will be 300, no doubt 300 kVA. But if I look at the voltage rating, 400 whatever we are mentioning is per phase. Similarly, 230 what we are mentioning is per phase. So when I am looking at a star connected transformer, it becomes per phase multiplied by √3, because we always mention it in line voltage configuration, not in phase. So I will have to call this configuration as 400 multiplied by root 3 divided by 230 multiplied by root 3 volts. So the primary line voltage becomes 400 times root 3 and the secondary line voltage becomes 230 times root 3. So correspondingly I would be able to calculate the current as well. So when I calculate the current, I can take what is the overall kVA rating divided by root 3 times VL, where VL is the line voltage. Or if it is star, I know for sure, I can definitely calculate what is the single phase current also. That will go as the 3-phase line current as well. If it is delta, of course I have to multiply the per phase current by root 3, right? So I should be able to easily calculate the 3-phase units rating in terms of voltages and currents based on in what connection I am making it. So let us say I have one single phase unit, something like this. So this is one single phase unit I am showing, right? And I am assuming that I am actually looking at the voltage rise in this particular direction. So I am going to mention this as dot. Generally the dot indicates the polarity of one winding vis-a-vis the other winding. So the other winding, if I show again a dot here, that means if I call this as positive with respect to this, this will also be positive with respect to this. So when I have two mutually coupled coils, I would show the dot probably in one winding as well as the other to specify that the polarities of both these windings are the same at that particular instant. Please remember, what we are applying is an alternating voltage. So as a rule, I can't have the top terminal to be positive and bottom terminal to be negative. All the time that will not happen because it is alternating voltage. So I am going to have clearly the positive and negative alternating. But I am talking about one particular instant. Maybe let me call that as the positive half cycle. During positive half cycle of the alternating voltage, I am essentially looking at this being positive. So this is being positive and this is being negative. At the same time, this is going to be positive and this is going to be negative. So let me draw the second phase also. So I am going to have the second phase here like this and the third phase here like this. Right? All three of them, I expect them to be identical when I want to connect three single phase transformers as a 3-phase transformer unit which is balanced in nature. Clearly we do not introduce unbalanced deliberately. We will not. We will try to make it only balanced. So all the 3 transformers have to be balanced. Now if I want to connect them in delta, I have to make sure if I say that this is the beginning of one winding, this is the end of that winding. Again similarly, this is the beginning, this is the end. And this is going to be the beginning and this is going to be the end. Right? If I want to connect them in star, all beginnings have to be connected together, all ends have to be connected together. One of them have to be connected together and the other end will come out. So that the beginnings connected together will make the star point or neutral point, or the ends connected together will make the star point or neutral point. Only thing I have to make sure this, that if this is dot, this is also dot, then only I can mark them as beginning and end. Clearly, I am looking at all of them rather tested for their polarity ultimately. So if I call this a star with a dot, similarly this is also a dot, I am going to connect them in star, in which case I have to connect this beginning to this beginning and this is connected to this beginning. Right? Now I will just bring out this terminal. This is the other terminal. This is the third terminal. So I am going to call this as, this will be connected to A phase voltage. This will be connected to B phase voltage. This will be connected to C phase voltage. Right? This is how they are going to be connected. Now on the secondary side, for some reason, if I want to connect it in delta, Delta connection always connects beginning to the end and so on. They are all connected in series addition basically. So I am going to connect actually this and this together. This and this together. Similarly this and this together. Now I am going to take out one terminal from here, second terminal from here and third terminal from here. So I may call these as A, B, C. So I have essentially connected the secondary in delta. So I can mention this a little differently or much more easily as though I have connected these things like this, and I am calling basically this as the star point, this as the star point and this also as the star point. So this is A, this is B and this is C. Let me call this as A dash, B dash, C dash. So in the secondary side, I can simply connect again somewhat like this. And then I may write this as A dash, this as B dash and this as C dash. And what is actually coupled with which winding? Which winding is coupled with which winding? That can be a little confusing, especially when we draw a configuration somewhat like this. This will definitely confuse the hell out of us as to which winding is coupled with which winding. So that is the reason sometimes we may draw, if the primary is drawn like this, we may draw the secondary somewhat like this. This is one secondary, this may be the other secondary, this may be the third secondary. Please look at the orientation. This is in vertical orientation. So if I may call this as this, then this is actually coupled to that. I can look at it that way. Similarly, if I am looking at this as one of the other primary, this is the other primary which is coupled to this. Similarly, if I am looking at this as the third primary, so this is the third primary which is coupled to that. So generally orientations in many books, they show the orientation exactly similar in the primary as well as secondary to show which is actually coupled to which one. Okay. So now I can again mention one is A, one is B and one is C. So whatever is this one, let me probably call this way. It doesn't matter. But one thing you guys have to understand is that the transformation ratio is always between phase voltages and phase currents. Generally, you never take the line voltages into consideration for getting the transformation ratio. What I mean is, if I am actually writing, for a three-phase transformer, maybe I just mentioned it is a three-phase transformer which is having 400 divided by 4000, volts. Okay, but it is connected in star delta. Let us say this is what is given, right? So what is given as the voltage is 400 is the line voltage in star. Similarly, 4000 is the line voltage in delta. So if I try to look at what is the phase voltage will be 400 divided by root 3. Whereas in this case, phase voltage will be 4000 volts itself. So if I try to calculate the transformation ratio for this transformer, I have to take actually V phase of primary divided by V phase of secondary or vice versa. V phase of secondary divided by V phase of primary. It doesn't matter. So I have to take this as 400 divided by root 3 divided by 4000. Are you getting this? Even though I write the voltages in terms of line voltages, when I calculate the transformation ratio, I will always take per phase. Unless I take per phase, it is not correct. It is incorrect. So we generally look at the per phase voltage ratios normally. We never look at the line voltages, although specifications will always, or nameplate details on the machine will always give the line voltages and line currents and 3-phase kVA rating. It will not talk about single-phase kVA rating. So ultimately, when we draw the equivalent circuit for a 3-phase transformer, we would always like to convert the whole thing into single-phase equivalent. We look at single-phase equivalent and then we will try to draw the equivalent circuit clearly in terms of single-phase configuration. So even though you may be given 400 volts star connected primary, you would like to treat that voltage as 400 divided by root 3. And if per phase impedance is given as some Z, you will always say 400 divided by root 3 divided by Z. That is what is the current. So you will always convert everything into per phase quantity and draw the equivalent circuit. So even if you are given a secondary winding in delta, you would again like to convert everything into per phase quantity, and that is how you will draw the overall equivalent circuit of the transformer. And when we are converting delta into per phase, it is probably easier to convert that into star and then do it in per phase. Most of the times that is easier. So you might like to do some star delta transformation before we really get into the per phase equivalent circuit of the transformer, when the 3-phase transformer is given in some kind of delta configuration somewhere. Right? Okay. So much so for 3-phase transformer. So I can have essentially 4 types of connections in the transformer. I would be able to get star delta or delta star or delta delta or star star. So these are the 4 configurations normally we can have in the 3-phase transformer connection, and I am showing this only by having primary and secondary. Sometimes there can be one more winding in the transformer which is known as tertiary. Tertiary winding is the 3rd winding sometimes you may have in a transformer. In especially power station transformers, we tend to have a tertiary winding mainly to supply the power station auxiliaries. For example, in a power station, you may have some protection systems. You may have a water pumping motor which is pumping the water into the boiler. You may have coal handling plant which will have n number of drives, maybe in pulverizing the coal, transporting the coal through the conveyor belt and so on and so forth. All of them need to be energized. All of them need power. So that power might come from the tertiary winding of your generator or power transformer itself. So sometimes we will have a 3rd winding which is known as tertiary winding in a transformer to make sure that it is able to provide the power for many of the power station auxiliaries. In which case, I have to show if it is a single phase transformer, I may have a core like this. One is secondary, the other one may be tertiary. This is like a 3-winding transformer. Are you getting my point? So I am having primary, secondary and tertiary. The tertiary might help in supplying the auxiliaries in the power station. Sometimes, if you look at some of your power supplies in the computer, SMPS, switched mode power supply, they may have small miniaturized transformer with multiple secondaries. It need not be just 2 secondary. It can be more than 2 secondaries. In which case, you may require a plus 5 volts for some of the ICs within your computer. You may require 3.3 volts for some of the ICs in your computer. You may require plus 15 and minus 15 for some of the analog electronic circuits. So these secondaries or these multiple secondaries might provide 5 volts, 3.3 volts, plus 15 volts, minus 15 volts and so on and so forth. So I may have multiple secondaries. And all these multiple secondaries will be isolated from each other. They don't have a common ground. That is a major advantage that we see when we use a transformer for providing different power supplies to different components in your laptop or in your computer system. So if we are looking at star delta, even if we are having 1:1 transformation ratio, that is phase voltage of star with respect to phase voltage of delta, if we are having 1:1 as the number of turns in the primary and secondary, still what we get here is, if we say that this is probably 400 volts, if it is 1:1, I should have gotten 400 itself on the secondary. But I am looking at phase-to-phase transformation. So 400 divided by √3 will appear as the line voltage in delta side. So I am going to have 400 volts is to 400 by √3. This is what I am going to get. So this is actually going to make automatic step down. Whether I like it or not, star delta configuration generally steps down the voltage on the delta side as compared to the star side, even if it is 1:1 transformation ratio, because it is phase-to-phase transformation ratio, and we are looking at delta being, or rather it is having the line voltage and phase voltages as equal to each other. So you are essentially going to have this as a step down configuration. Whereas very clearly this will be an automatic step up configuration. So what I get as the line voltage will be way too higher as compared to what I am going to get as the line voltage on the primary side, even if the transformation ratio is 1:1, right? And one more major point we have to mention about star delta and delta star is that if, let us say, I have, as far as star is concerned, this is VA, this is VB and this is VC. Let us say I have 3 phase voltages like this, right? If I want to look at the line to line voltage, for example, if I take C on the other side, this becomes minus VC. So this is going to be VAC. So the line voltages are 30 degrees shifted from the phase voltages, right? So we are going to have essentially a 30 degree phase shift between the phase voltages and line voltages. But what I am applying actually is a line voltage. I hope you understand, because we bring generally only 3 terminals out of a transformer. Whether it is star connected or delta connected, it hardly matters. Most of the times only 3 terminals come out. These 3 terminals are going to actually be connected to the 3 terminals which are coming out of your power supply, the 3-phase power supply. So what you are applying looks as though it is line to line voltage. But what happens between the primary winding and secondary winding is phase to phase transformation. So what I apply as the line voltage, which is actually here, is converted into transformed phase voltages as far as delta is concerned. If I am having primary as star, what I am applying is line to line voltage, and what I look at as the line to line voltage finally in the delta side will be similar to the phase voltage. So not only the voltage is stepped down, but it is also shifted from the original line voltage by 30 degrees. So star delta or delta star configurations will always give me 30 degree phase shift between one side and the other. I can say 30 degree lead or 30 degree lag depending upon what kind of line voltages I am looking at. For example, VAC is giving me 30 degree lag compared to VA. Whereas if I am looking at VAB, right, this is VAB. VAB I have to draw somewhere here. This is what is VAB. Whereas VAB will have 30 degree lead. So I can in general say 30 degree phase shift comes out between the primary line voltage and the secondary line voltage whenever I have either star delta or delta star configuration. But if I have a star delta configuration, even for 1:1 transformation ratio, I am going to see that the line voltages are stepped down by a factor of √3. Whereas in delta star configuration, the line-to-line voltages are stepped up. So I can say that these two configurations have a whole lot of significance when I am actually employing them in different applications. For example, if let us say I have a rectifier, I am going to show a rectifier just with the help of a block. Maybe this is my rectifier and I am applying a three-phase voltage, and what I am getting here is DC. So when I am actually looking at a rectifier output, I may have A phase, B phase and C phase rectified completely, right? So if it is a half wave rectifier, I may get only some voltage like this, right? It should actually overlap because it is 120 degrees only shifted from each other. So I'm going to have maybe a voltage like this, and voltage like this. This is half wave rectified. If it is full wave rectified, I have to again draw on the top of this also one more voltage, right? So I'm going to have some voltage like this, right? This is how it is going to be. So I have full wave rectified voltage as well as half wave rectified voltage possible with three phase. But if I am having one more three-phase rectifier with another 30-degree phase shift, so maybe this is fed by star, this is fed by delta. The primary probably is the same. The primary can be in star or delta, it doesn't matter. But on the secondary side, maybe I have one of them to be star, second one to be delta. Then they will have 30-degree phase shift. So if I say that this waveform is like this, for the next transformer it will be actually 30-degree shifted. If I am having actually two rectifiers cascaded, maybe connected in series or whatever, one of the rectifier is being fed by a star winding and the other one is fed by a delta winding. What I am asking you to imagine is, let us say the primary is a star. In the secondary, I have one star and one delta. So I am connecting this delta here and I am connecting this star here. So what will happen? They will have voltages which are 30 degrees shifted from each other. Of course, I have to take care of the turns ratio. If I don't take care of the turns ratio, one voltage will be 1 by root 3 times the other voltage. That's not right. I don't want to have different voltages. I want to have the same voltages, but they are 30 degrees shifted from each other. So which means I am going to have actually a waveform which will have much less variation. So originally maybe my waveform was like this. Now what will happen is, in between the two also I will get another portion of the sinusoid like this. So overall voltage will look as though it is having very little variation. It is going to have really little variation because of the fact that I am adding up two waveforms which are alternating, no doubt, which are rectified, but they are phase shifted from each other by 30 degrees. So delta star and star delta transformers have plenty of applications like this because of the fact that they inherently introduce 30-degree phase shift. That actually reduces the ripple or the variations in the DC voltage by actually getting two phase shifted waveforms which are away from each other by 30 degrees. Right? Got it? So if we go back to our original configuration of delta delta and star star, these two will neither have step up nor have step down inherently, because they will translate exactly whatever voltage you are applying from the primary side into the secondary side. So you are going to have essentially, no phase shift at all in this particular case. And you are also going to have basically, if I look at the line voltages as well as phase voltages, they will look exactly the same. There is no problem at all. No phase shift, no step up or step down. both are true in this case. In delta-delta configuration, normally major advantage, I am just trying to compare different configurations. That's all I am trying to do. Delta-delta configuration, one major advantage we have is we can actually, if one of the single phase transformers conk out, we will be still able to operate it as an open delta or V configuration in case of one of the transformer failing. What I mean is, let us say I have the three-phase transformer here in delta like this. Maybe this is my primary and this has been my secondary. Right? And let's say one of these configurations, maybe this has conked out for some reason. One phase has conked out. Maybe the transformer has been having some fault. Right? In which case, what I can do is, I can apply the same ABC here and I can, ABC here, and I can eliminate this particular winding. So I can eliminate this winding, and similarly I would be able to connect the load here. I can eliminate this winding completely. Similarly, I can eliminate this winding completely, and I would be able to connect the load, maybe connected in star or delta here, basically. So these are the loads. Please note that it is a star connected load that I have shown, and ZL is the impedance per phase. Right? So when I eliminate one of the windings, still the transformer will be able to deliver a fairly good amount of kVA rating, which should be close to 2/3 of the original value of kVA, but it will not be exactly 2/3, it will be slightly less than that, because originally what you were looking at was the phase voltage and phase current. Between those two, whatever was the displacement, that was coming as the power factor angle alpha or phi. Whereas now it is line voltage. Please note that this is not really contributing any current. This is absent. So what is the current flowing is only this current. And that is essentially the phase current, which is manifesting itself as the line current. So what I have is line voltage and phase current, or phase voltage and line current here. I can say if it is delta and star. So I'm going to have phase voltage and line current, which will give me a phase shift of 30 plus phi or 30 minus phi, like 2 wattmeter method. What we did in the case of 2 wattmeter method, it will become very similar to that. Because of which the power factor angle is kind of modified in this open delta connection. I am not planning to go into great detail about open delta connection. All I want you to understand is, if it is delta-delta configuration, although there is no phase shift, although there is no step up or step down, the major advantage, one single advantage of delta-delta configuration is, even if one of the transformers conk out, I should be able to operate it at a reduced kVA rating, because it can functionally work properly as a three-phase transformer, despite one of the transformers being opened. So we call this as open delta or V connection, because this is like a V. So we call this as V connection or open delta connection. So this can work at reduced kVA rating as compared to the original three-phase. Fine. The last one which we have still not discussed is the star-star case. As far as star-star is concerned, it is again no step up or step down, no phase shift, but this is one of the rarest configurations that are used anywhere. Unless I ground the neutral. If the neutral is not grounded, it is not really a popular configuration that is being used. Let's see why. Why star-star configuration without neutral grounding cannot be used very easily. What is the problem with this? Let us try to take a look. So, if I am having, let us say, a star-star transformer, I am looking at mainly the primary. Okay? Let's say secondary is open. I am not really looking at it right now because it is open circuited. So, I am looking at no load condition. Under no load condition of this particular transformer, this will definitely draw magnetizing current. Each of these phases are going to draw magnetizing current. So, let me call this as IMA, maybe IMB and IMC. So, these are the three-phase magnetizing currents that are being drawn. This is open circuit condition. So, I am not even talking about load. Load current is not present. And we saw that because of the property of iron, which is the core of the transformer, the magnetizing currents are not sinusoidal. They are non-sinusoidal because hysteresis is there, saturation is there. So, I am going to have definitely non-sinusoidal currents. So, I would say that first of all we should recognize the fact that magnetizing currents are non-sinusoidal. If they are non-sinusoidal, generally we actually expand any non-sinusoidal periodic waveform by something called Fourier expansion, right? So, the Fourier expansion will allow mathematically a non-sinusoidal periodic waveform to be decomposed into some fundamental which is corresponding to 50 hertz in this case, then maybe 2 times the fundamental, 3 times the fundamental, 4 times the fundamental and so on. So, you will have multiple harmonic components. We call these as harmonic components, which is second harmonic, third harmonic, fourth harmonic, fifth harmonic and so on and so forth. So, we are going to have this non-sinusoidal magnetizing waveform being decomposed into 50 hertz, 100 hertz, 150 hertz and so on. And as the harmonic increases, the number increases, that is if you go to 5th, 7th, 9th and so on, all of them are going to be smaller and smaller as compared to whatever was your fundamental, because your primary thing, the waveform that you have generated itself is corresponding to 50 hertz. So, as you go to higher and higher order harmonics, generally it will be decreased or diminishing proportionately. So, if I am looking at this waveform, it will definitely have the dominant component as 50 hertz. Next to that it should have been 100 hertz. But 100 hertz essentially is something similar to DC. On an average basis, it will be 0. So, any even harmonic is very similar to 0th harmonic, which is DC. If the average value is 0 or the waveform has above the time axis and below the time axis, if it has the same half-wave symmetry, then you are going to have all the even harmonics being absent. So, you will not have 4th harmonic, 2nd harmonic, 6th harmonic, 8th harmonic, all of them are absent because of half-wave symmetry. DC is also absent because average value is 0 in an alternating current waveform. So, what we have as the lowest order harmonic is 3rd harmonic. So, lowest order harmonic is actually corresponding to 3rd. Whereas fundamental of course is very much present. So, if I try to write IAM, I should write that actually as, rather I should write this as small IAM because instantaneous current magnitude. I should say IA1 may be cos or sin omega t plus IA3 cos or sin omega t, but that is 3 omega t. This will be IAM. I am neglecting the 5th, 7th, 9th, 11th and so on and so forth. I am neglecting all of them. I am looking at only the fundamental and third harmonic. Similarly, if I look at IBM, so let me write IAM here, which is actually IA1 cosine omega t plus IA3 cosine 3 omega t. Similarly, IBM will be IB1 cosine omega t minus 120 degrees because it is three phase. Similarly, this will have IB3 cosine 3 of omega t minus 120 degrees. And similarly, ICM will be IC1 cosine of omega t plus 120 plus IC3 cosine of 3 times omega t plus 120. Right? Now, when I look at the star connected system, I have IMA, IMB and IMC and the neutral is not connected. Right? So, IMA plus IMB plus IMC equal to 0, I am perfectly fine. If IMA plus IMB plus IMC is not equal to 0, I have to provide a path. And to provide a path for that current, I have to connect the neutral to ground or somewhere. If I don't connect the neutral, I will not be able to allow the third harmonic to exist. Let me look at it here. If I actually look at what is, see, we are essentially looking at the oscillation of the current at 3 times the frequency. The phase shifts will be maintained exactly as it was being maintained originally in the waveform. That's how it will be. If you actually try to decompose into Fourier expansion, the way you get actually these components will be whatever is the original phase shift, that will be preserved with a factor of n, where n is the harmonic order. That's how it is normally. So because of which you are going to have all these 3 as co-phasal, because 360 degrees is actually, you are not going to have any phase shift at all. So if you look at the third harmonic for A phase, third harmonic for B phase, third harmonic for C phase, you are going to have cos 3 omega t minus 360, cos 3 omega t plus 360, which are co-phasal. If they are co-phasal, they will not add up to 0. It is not going to add up to 0, whereas these add up to 0. These add up to 0. Whereas because they are co-phasal, the sum is not equal to 0. So what is going to happen is, if I am having a star-star connected transformer, neither the primary is grounded nor the secondary is grounded. In which case, especially when I am initially energizing the transformer, I just turn on the power supply, I have not connected the load. At that point, the primarily drawn current is magnetizing current. Core loss component of current is definitely there, I am not questioning that, but that is mainly the magnetizing current. That magnetizing current is going to always have harmonic components, and especially third harmonic is not going to find a path for itself to flow, because if I try to look at the neutral current will have a non-zero third harmonic component. And there is no path for the neutral current. So where will the current flow? It cannot flow anywhere. If the current cannot flow anywhere, it has to cease to exist. It has to kill itself. There is no other way. So the current has to be primarily sinusoidal. It may have fifth harmonic, seventh harmonic, but those are minuscule as compared to third harmonic. So the third harmonic current cannot exist in a magnetizing current of the transformer which does not have its neutral grounded. If the neutral is not grounded, especially in a star-star configuration, I am not going to be able to find third harmonic component in the magnetizing current. If third harmonic component is not there in the magnetizing current, it has to be fairly sinusoidal. If the magnetizing current is sinusoidal, then the flux cannot be sinusoidal because they are not linearly related. Right? The hysteresis loop tells me, the magnetization characteristics tells me that I can't have linear relationship between magnetizing current and flux. The flux cannot be sinusoidal. So I would say if neutral path is not provided, then third harmonic is zero, or third harmonic cannot exist. If third harmonic cannot exist, I'm going to have magnetizing current becomes sinusoidal or cosinusoidal, it doesn't matter. If magnetizing current is sinusoidal, I can say flux and Im are not linearly related. So, the flux is non-sinusoidal. I don't know what wave shape it will take, but I can say it is non-sinusoidal. If flux is non-sinusoidal, induced EMF will be non-sinusoidal because it's after all d phi by dt. So I'm going to have d phi by dt or induced EMF will be non-sinusoidal. So what is happening now is, in a transformer, we said V is equal to E, where V is the applied voltage, E is the induced EMF. That is completely lost. Are you getting my point? I am applying sinusoidal voltage. It is supposed to draw a non-sinusoidal magnetizing current, but it is forced to draw a sinusoidal magnetizing current. Because it is forced to draw a sinusoidal magnetizing current, I am going to have a non-sinusoidal flux. And that non-sinusoidal flux is going to induce a non-sinusoidal EMF. That non-sinusoidal EMF and the sinusoidal voltage that I am applying cannot really balance each other. There is going to be a voltage difference between the induced EMF and the applied voltage in a transformer which is star-star connected, whose neutral point is not grounded, and currently it is on no load condition, and this will cause huge amount of oscillations or very large currents to be drawn in spurts, because of which the transformer can malfunction. So I would not like to normally use a star-connected transformer, star-star connected transformer without the neutral being grounded, unless I provide some path for the third harmonic current. If I want to provide the path without connecting the neutral, right, I might like to have a tertiary winding in delta. It can very happily have a circulating current, who cares? If I have a secondary winding or a tertiary winding in delta, secondary winding already I said is star, star, star. So I can have a tertiary winding in delta. So sometimes the tertiary winding serves this purpose in a transformer. If it is a three-phase transformer, star-star connected, without neutral grounding, there can be a tertiary winding connected in delta, which can simply circulate the third harmonic current. The third harmonic current being cophasal, IA3, IB3 and IC3 are exactly of same magnitude, exactly in phase with each other. So it would be able to simply circulate itself through a delta. So I don't have to use the tertiary for anything, just for circulating the third harmonic current, which will restore the balance. Right? Thank you.